So far I've been okay with the idea that planets are in circular motion around the sun, or that the moon is in circular motion around the earth, but in the late 1600s, early 1700s, there was a German mathematician, wannabe astronomer, and his name was Johannes Kepler. And he was asked to do some observations about the planets we can see with our naked eyes, which we can actually see Mercury pretty easily, and Venus for sure, and Mars and Jupiter and Saturn. Jupiter and Saturn are far out, so they move really slow. They don't change their position that much. But Venus and Mercury change their position a ton. And if, for example, the Earth around the Sun were a perfect circle, if the Earth going around the Sun were a perfect circle, well then something would be true. If you looked at the speed at any moment, it would always be the same. Obviously the velocity vector points in a different direction, but the speed would always be the same. So if your orbit were circular, the speed would never change. But Kepler noticed something very important looking at the orbits of Mercury and Venus. What he realized was that at some times they were faster, and sometimes they were slower. But what that means is that, guess what? They can't be perfect circles, because a perfect circle would always be the same. We know this because the speed is determined by the force, and if the distance were always the same, the force would always be the same. So what does that mean? If it's faster or slower, the radius of orbit can't always be the same. And so what Kepler came up with, he was a mathematician, he realized there's another shape that might satisfy this. And what he realized was that the planets don't actually go in circles, they actually go in a different shape called an ellipse. Now an ellipse is basically a mathematical oval, and I'll draw a type of ellipse here and I'll tell you what it means to be an ellipse. So if you're an ellipse and you look like this, for example, there are 2 points inside the ellipse that are actually really important. There's a point down here and a point down here, and these are called focal points. Some people call them the foci or the foci. Let's just stick with the focal points. And this one looks really flat, like almost like a pancake shape. Different ellipses are more circular. If I can get another one here, let's see if I can draw one here. That's not too bad. What's going to happen here is that your focal points are going to be in a little bit farther. Get rid of this guy. The distance between your focal points determines how flat your ellipse is. So as you take these and you stretch them out, your ellipse will get flatter and flatter. Same thing here, right? And if you move them closer and closer together, it gets more circular. In fact, if we were to look at an ellipse where both focal points were right on top of one another at the center, now you would have your circle. So an ellipse is like a circle. A circle is an ellipse, but not all ellipses are circles. So this is a circle where the focal points are right on top of one another. But what does it mean? What does it mean to be an ellipse at all? Well, here's what it means. If I were to pick any random point on here and walk from one focal point to my point out here and then to the other focal point. So we'll call these, this is point, we'll call this one A, and we'll call this one B, and we'll call this point C. If I were to walk from A to C and then C to B, so A, C plus C, B, we'll make these distances, right? Well, if I were to switch to a different point on the ellipse, and it doesn't actually matter any point, If I go here, for example, we'll call this D, and I'm going to then walk from D to B. If you're paying attention, you will notice that this distance is shorter, but this distance is longer. And all of a sudden I see like, oh, well, what about this AD plus DB distance? What do you think is true about those? Well, of course they're equal, because that's how cute and fun math is. And if I picked a point down here, E, for example, I would make my first trip distance longer, but you notice that my second trip distance is shorter. So AE plus EB, all these are the same, and that's what it means to be an ellipse. Okay? Another term they use is they call it eccentricity. The eccentricity of the ellipse. The flatter it is, the more eccentric. So, for example, this one here would have 0 eccentricity, and then it approaches 1. So eccentricity it goes between 0 to 1, and 0 is a circle and 1 is an infinitely flat pancake shape. Now, what Kepler decided was that, oh, well, all planets orbit the sun, not necessarily in circles, although they could be circles because that is an ellipse, but not really in circles, they're more in these ellipses. Now, this is an extreme ellipse, so we're going to come back to this one in a moment. Let's get rid of this. What he decided was that all planets orbit the sun in ellipses where the sun is at one of the 2 focal points. And that's like the important thing. All planets orbit the sun in ellipses with the sun at one of the 2 focal points. So let's try to draw another ellipse here. Okay? I don't want it to make it too extreme like this. Comets, like Halley's Comet or Hale-Bopp, they orbit like this, where the sun would be here. Let's try to get a kind of semi-round, see if I can do it here. Ugh, ugly. Alright, that's good enough for government work. So, here's a planet, it's going around the sun. The sun is at one of the 2 focal points. Let's put this focal point right here. Here's the sun. So what does that mean about our planet? It's cool because as the planet comes around, like we'll take the 2 extremes for example. Here it's farthest away, here it's closest. Here the velocity is small, here the velocity is super big. And then in between here, for example, it would be tangent, and in between. And of course out here, same thing, it would be tangent. And so this one's small, this one's large, and then in between. So all planets orbit the sun in an ellipse with the sun at one of the focal points. Slow when it's far away, fast when it's close, and that's Kepler's first law. So that's cool. It's actually a really interesting thing in terms of the fact that even if it were totally circular, it would still fit. But because all the distances are the same, we could have the constant speed. But as soon as you move that sun out of the center, it's going to be closer here, faster, and then slower. We call this the slingshot, right? Slow out here, and as it gets faster, it spins around, and then goes slow out here, and then spins around. Kepler's second law is actually just an extension of the first law. In that we still have the faster, slower thing. I'm going to draw a better one. That was ugly. We still have the faster, slower. Well, watch what happens. I'll draw another ellipse here. That'll do. So we're going to take, whether it's a planet or a comet, it doesn't really matter. It's easier to see this with comets anyway. We're going to put the sun at one focal point again. And let's say this is a comet this time. Okay. Well, what happens? I'm going to take a time, we're going to say a time, let's say it takes 20 years for this comet to go around, right? So it takes 20 years. It's moving fast here and it's moving slow here. If I start looking at it, well, how much distance is it going to take up in 1 year? Well, in 1 year, it may go from here to here because it's moving really fast. But when it's out here, it's going really slow. So 1 year might only be this distance here. So we don't have equal distances because the speed is different. But watch this. If I were to draw a line from the center of the sun out here, this line would sweep out this area here. If I color in this sector, but look at this one. This one here, if I do this whole line thing from the center again, what do you notice? This distance is much smaller, but it's much farther away. So what do you think is true? You think the areas are equal? And they totally are. So a line drawn from the sun to a planet or comet, in this case we're using a comet, but it's true for planets too. Alright, this is the important part. Sweeps out equal area in equal times. So in our scenario here, I said, well, this is, 1 year. Distance goes here, but this is also 1 year. The distances are not the same, but the areas are. Now, what does that mean for us? Well, these are objects that are going, basically they're orbiting around, true? So if they're orbiting around, chances are they have angular momentum. Do they not? So if we think about angular momentum, so we use L for angular momentum. We either use a little l or a big L. I'll use a big L here. Angular momentum is equal to, in general, it's equal to I omega, where I is the moment of inertia and omega is the angular velocity. And so what does that mean for us? Well, because the sun and the planet are far away, we can assume that the planet is a point particle, therefore I is equal to mr squared, where m is the mass of the planet and r is its distance, center to center distance, and omega, oftentimes we can express this as v over r. True, we've seen this before. So the question is this. If I look at my planet, or my comet, or whatever, as it's going around the sun, and I want to compare what it looks like here to what it looks like here, how many times faster is it between here and here? Well, let's do a little bit of a deeper dive into here. We're going to examine it here at its closest, or examine it here at its farthest away. And the way I have it drawn here, if we call this distance r, how many times farther is this? Like 1, 2, 3, 4, we'll call it 5 times. So we'll say that this is r here, and this distance here is 5r. I want to know how many times faster is it when it's close than when it's as farthest away? That's a great question. If you're paying attention, you'll have a sense that, well, it could be easy because it's 5 times as close, it could be going 5 times as fast. But it could be a squared relationship, so it could be going maybe 25 times as fast, or maybe it's going root 5 times as fast. It's hard to know. Not if we apply our angular momentum principle. The thing about angular momentum, as long as there's no external torques, the angular momentum is conserved. And there can't be an external torque because all the forces are always perpendicular to the velocity direction. So that's cool. So let's talk about this. That means that L, when it's close, we'll say when it's close here, we'll say that's point A right here, and then when it's far, we'll say it's point B. The angular momentum at A has to be equal to the angular momentum at B. So what does that mean? Well, if I apply this principle here, I know that I A omega A is equal to IB omega B. So we still have the angular momentum as being equal. If I substitute my angular momentum, or if I substitute my moment of inertia and my angular velocity in here, I end up with mr squared times v over r is equal to, this is A, and this is A, and this is A, is equal to mr at b squared times v at b over rb. Okay. Cool thing is if I look, this is r squared over r, one of those is going to magically disappear. The m on both sides magically disappear. And I end up with a cool expression. The r at a times the v at a is equal to the r at b times the v at b. And what do I notice from my diagram here? I notice that the r at b is equal to 5 times the r at a. So if I substitute that in here, I end up with r a v at a is equal to 5ra times v b. And we can see that we have the RA's on both sides, so the velocity at A is equal to 5 times the velocity at B. So it turns out it's the easiest of the three understandings, is that if you are 5 times as close, you are moving 5 times as fast.